Hello, a short video this week showing a fast and simple approximation of the sine function. If you're watching this video, I'm going to assume you've already searched Google for approximations of the sine function and are well aware of the several techniques that other people use for different platforms. So I'm going to leave all of the caveats and the use cases of this approach to the end of the video and just get stuck in with the guts of it now. Now, if you've watched any of my previous videos on sound synthesis, you'll know that we use the sine function a lot, and it's usually used in this sort of format, where we take the volume times the sine of 2 pi times the frequency of the sound that we want to play times time. And this is great when you have a processing architecture that has the facilities to do these functions. However, my plan is to migrate some of the synthesis code to an embedded systems platform that doesn't have in-silicon sine computation. It also has a reasonably low clock frequency, so I need something that's fast and simple, and because it's audio synthesis, an approximation to sine is sufficient. So I'm going to start just by defining the scope of the sine function we're trying to approximate. And the assumptions I'm going to make is that the frequency is always greater than or equal to 0, and the time is always greater than or equal to 0. So the final form of our sine function is going to be simply y equals sine of x, where x must be greater than or equal to 0, and of course y, our output, is going to be from -1 to +1. For the uninitiated, this is a sine wave, and here we've got it crossing the axis at pi, 2 pi, 3 pi. In fact, it'll do that forever and ever and ever. It goes on, and this is periodicity. And so our approximation will also need to handle this periodicity. And that can be quite complex. Now, assuming we're using floating point, one way to handle the periodicity would be to use something along the lines of a floating point modulus function, which would take our x input and we could modulate that by 2 pi, which of course means for every value over 2 pi it wraps around to 0. So we can use basically the remainder as the index into our approximation function later on. However, this function is complex, requiring a floating point divide, and it may not be supported on all platforms, and I think there's a better way to do this. And what I'm going to do instead is normalize the input to between 0 and 1, of course, by dividing it by 2 pi. In this case, I want to keep it no divides because they're usually quite complicated to do, so I'm going to multiply it by a constant 1 over 2 pi. So this means now 2 pi is equal to 1, and 0 is equal to 0, and pi is equal to half. And instead of requiring us to do some arbitrary modulus to some complex number like this, instead we can simply hack using an floating point to integer conversion. So we can take our normalized value and subtract from it the integer value instead. So this will always give us a remainder between 0 and 1. And just in case your language doesn't support this, it's the equivalent of using, say, the floor function. If I graph what this looks like, we'll see it remains a sine function, but it looks like a high frequency. And here I've just zoomed in on it. We can see the original sine wave in the background and the new y equals sine 2 pi x here, where the input of x is scaled by 1 over 2 pi. We can see it crosses now at 1 and half, and so forth along. So now we've got this easy way of calculating the remainder without using the floating point modulus. I'm going to show two approximations, but I'm going to start off with a quadratic approximation to sine. To calculate this, I know that my roots for at least one of the parabolas is 0 and 0.5. So let's just start with a very basic quadratic calculation with a root at 0 and a root at 0.5. First thing I can see is it's upside down, so I'll throw a minus sign in there just to invert it the right way up. And so we can see it crosses now at the same places, but it needs some scaling. I'm just going to take a guess at the scaling, and we'll say it's 10. Oh, that's not quite enough, so let's try 20. That looks a bit too much. Let's try somewhere in the middle. 15, no, 16. Oh, that one looks good. So let's just quickly zoom in, and we see it's absolutely perfect. So it gives us a value up to a maximum of 1. That's handled the positive side of the sine wave. Let's now look at a quadratic equation for the negative side. So we know that we've got a scaling factor already, and we know that we don't need it to be minus 16 this time. Probably 16 will do, because it's a parabola that's the right way up. But our roots have changed, so now it's 0.5 and 1. There we go. So using two parabolas, we can roughly approximate the sine wave. And we can see it is an approximation. It doesn't perfectly follow the purple sine wave in the background, but you know what? It's probably good enough for audio synthesis. And we can decide which equation to use based on the input value of x. If it's greater than 0.5, we use our positive parabola, and if it's less than 0.5, we use our negative parabola. Let's just have a look at the numbers here. So if we just copy over our first half, which was minus 16, x take 0, and x take 0.5 for our roots, and if we just tidy this up a little bit, we've got minus 16, x squared, take 0x, take 0.5x, and the constant disappears, 0 times 0.5, that goes away, and we fill that out now to be 16 minus 16x squared, take 8x. And programmers get very excited when they see 16s and 8s and 4s and 2s because it usually means there's some scope for some bit field manipulation to more optimize the mathematics involved. Now we're doing this all in floating point, but if I did want to convert this to a fixed point, of course multiplying by 16 is the equivalent of shifting 4 bits, and multiplying by 8 is the equivalent of shifting by 3 bits. So there's potential for optimization here. Let's also consider the other half of our parabola, which was 16x take 0.5 and x take 1. And if we expand this out again, we've now got x squared take 0.5x take 1x plus half. Now I'm not going to group up the 0.5 and the 1 for exactly the same reasons as labelled above, because if we draw this out now by multiplying everything by 16, we get our 16x squared take 8x take 16x plus 8. And again we remain with coefficients here which are multiples of 2. Here I've drawn out the pseudocode for our approximate sine function. I'm going to assume that we're using 32-bit floats for all of this. And here we can see that I first of all scale the input to normalize it between 0 and 1. I then do this nice way of doing a modulus just by taking the integer proportion away from the input. And it's just then a question of making a decision between which parabola you use, whether we want the first half or the second half. So here I've overridden the sine function in my synthesizer with the approximate sine function you've just seen me type out. And I'm going to play it and we'll have a listen. So this is just a pure sine wave. So this is what a sine wave sounds like in this system. And now if I remove the sine and replace it with our approximation, it's not a bad sine wave. It does actually sound like a little bit of a square wave. And if we look at the graphs, we can see why. Our approximation, the black line, is always larger than the actual sine wave itself. It bulges out. So it's approaching a square wave. Very slightly. That said, I think it's quite a good approximation. Now I'm sure there'll be some programmers out there that really don't like having a branch condition in the middle of their continuous function approximation. One way to do this would be to use an approximation that has 3 roots instead, so a cubic. And I suppose it would look something like this. So we would have y equals x minus 0, because we know that's one of our roots. We know the next root is x minus 0.5, which would be equivalent to pi in our normalized space, and x minus 1. Let's take this over to the graphing platform and have a look. So our first root is at 0, our second root is at 0.5, and our third root is at 1. And we can see the roots are fine, but again we've got a scaling issue, so let's just have a quick guess. I'm sure there's some maths purists out there that might be able to work this out. 15 is not quite enough, 20 is not quite enough, 21 is a bit too much. So somewhere between there. In fact, I know it turns out that 785 actually gives us a precise 1 for the output. Now using exactly the same periodicity calculator that we used for the quadratic, we can use the same for the cubic, and we can see that this time the peak happens before the sine wave and the peak happens after the sine wave. And so by definition, this approximation is not so much a sine wave, but it's a very slight sawtooth wave, and so we must listen to it. So here in exactly the same function, you can see I've just typed in the code exactly. I've not tried to reduce it to look at any interesting coefficients that we might be able to optimize further. Let's have a listen. Now that sounds absolutely lovely. There's just something really nice about that tone. If it sounds a little bit garbled, that will be down to the YouTube audio compression. So I recommend that you get the code from GitHub, follow the link below, and try it out for yourself. At the start of this video I mentioned that there are always caveats when approximating other functions. For really large values of x, the floating point precision would start to work against you, which may produce some very interesting audio artifacts, perhaps a gradual degradation of the audio quality over time. It might sound really cool, but it's always worth thinking about the use cases for your approximation. On a modern desktop computer, you're probably better off just using the sine directly. There'll be dedicated silicon on the CPU for processing sine and cos and tan and all the others. Popular methods in times gone by were to use lookup tables that did the approximation for you. However, on modern architectures these are probably more likely just to pollute your cache and won't be faster than just calling sine directly. On embedded systems you've always got the trade-off, because if there is a floating point processor on there and it doesn't have sine, then you're going to need an approximation such as what I've shown today. And a lot of embedded systems do have floating point support for multipliers and addition, but don't have more advanced trigonometric functions. But it's a trade-off. You have to question the virtue of using floating point on such a platform when a fixed point approximation may do instead. I hope this video has shown you just how easy it is to approximate functions. If you'd like to give us a thumbs up, subscribe and check out the onelearncoder.com blog. See you next time.